Alright, continuing on physical chemistry, chapter 17, we're beginning section 3. Section 3 is a pretty long section. We're going to be integrating rate laws for different order of reactions. We're going to start out with a zero order reaction. Yes, there is such thing. It's very uncommon, but it does happen. One example would be enzyme catalysis. You've got, let's see here. Well, that's about all we're going to say. Take biochemistry if you want to learn that. So anyway, here's the reaction we're going to say. We just have this substance A, this A is the nu, stoichiometric coefficient, goes to the product or products. And then, so our rate law is going to be R is K times the concentration of A to the zero. This is not not for standard state. This is zero power, because this is a zero order reaction. A to zero is just 1. So our rate is just K. So if you graph rate versus concentration of A, or time actually, it's a horizontal line. The rate is always just equal to K, the constant. Now, remember we showed before how our rate, by definition, is always, for any reactant, minus 1 over A times the differential of the concentration of A divided by the differential of T. And this is going to be equal to constant for a zero order reaction. Remember, T is time, lowercase t is time. Now what we want to do is get the variables on one side, so we're just multiplying by A, etc. So we have minus the differential of the concentration of A is equal to this A, your stoichiometric coefficient, times the constant K, times the differential of T for time. So we're going to integrate the concentration from the initial concentration of A, which won't be zero, remember, since it's a product, you're going to start with a max and it'll go down over time, to your final concentration of A, of minus the differential of A. And that's equal to AK. These are both constants, so you pull those out. The integral from 0 to T of the differential of time. We're also going to find a new constant here. So if you take this A times the constant K, that's going to be just K subscript capital A for the substance A. Okay. So the integral of minus the differential of A is just the concentration of A. So we're going to evaluate minus the concentration of A from the initial concentration of A to the final concentration of A. And then likewise the integral of 0 to T, just the differential of T, is just T. So we're going to evaluate that from 0 to T. So this is going to give us minus the concentration of A, minus the negative for plus. Oh shit. Awesome timing. Anyway, plus the concentration, the initial concentration of A equals Ka times T minus 0. And of course, so that'll just become T. So we'll switch these around so you have a minus sign. So you have the initial concentration of A minus the concentration of A is equal to that constant we defined times time. And this is one form of the integrated rate law. And this is only true for a zero order reaction. Continuing on physical chemistry, chapter 17, we're in section 3. We're still talking about zero order reactions only. So we can't come up with the integrated rate law for a zero order reaction, and then just solving for the concentration of A, we get the concentration of A naught minus Ka times time. So if you were to graph A naught minus the concentration of A, the initial concentration of A minus concentration of A against time, you're going to get a slope. A straight line. It's going to come from the origin, and the slope is going to be, Ka. And this is only true for zero order reactions still. Now if you were to just graph concentration of A, remember that'll start up here. I think that actually should start at the line here. So it's going to start up here at your A naught, and then continue down over time. And the slope is going to be equal to minus Ka. And as an example, I said before that enzymes, they'll have a zero. They'll cause zero order reactions. Likewise, if you have a reaction on the surface of a solid catalyst besides just an enzyme, that can be zero order also. Okay, continuing on chapter 17, section 3, we're integrating rate reactions. Anyway, now we're doing first order reactions. These are very important reactions, partly because they're very common. For example, all nuclear decay, those are always first order. Now, for now, we're just going to say, okay, we have the reactant, A, it goes to product, or one or more products, doesn't really matter, because the reaction rates are almost always based on the reactants anyway. Now, remember, we showed from before, the rate of reaction R is equal to minus 1 over A times the differential, the concentration of A with respect to T. And it's minus because A is a reactant. And since it's first order, we've got K times the concentration of A to the 1. Obviously, you can leave the 1 off. Now we want to integrate this. So first thing we're going to do, let's see here, what did we do? Oh, we just multiplied by A. So we have the differential of the concentration of A divided by differential of T, and then we got the minus sign over here too. So we minus A times K times the concentration of A. And remember, just like before, we're going to take these two constants, A times the K, and make that just one constant, K sub A. So now we've got the differential of the concentration of A divided by the differential of time is equal to minus the concentrate, or the rate constant for A times the concentration of A. Now we want to separate the variables, so we're going to get A on the left and everything else on the right. So we have 1 over the concentration of A times the differential of the concentration of A, and that's equal to minus the constant for A, the rate constant for A, times the differential of time. Now we can integrate this. Continuing on physical chemistry, chapter 17, section 3, everything you see here is for first order reactions. So I showed you before how we had the rate for the first order reaction and we wanted to integrate it. So here we are integrating it. We're going to integrate from the initial concentration of A to the final concentration of A of 1 over the concentration of A times the differential of the concentration of A equals minus Ka times the integral from 0 to T of dt. So integrating 1 over the concentration of A, that's the natural log of the concentration of A. We're going to evaluate that from the initial concentration of A to the final concentration of A. And then integrating 0 to T of just dt, that's just T, evaluated from 0 to T. And then I'll spare you a couple algebra steps. You have natural log of the concentration of A divided by the initial concentration of A. Notice these have the same units, so you're taking natural log of just a ratio. There's no units for that natural log. And that's equal to minus the constant for A times T. This is the rate constant. And this is, of course, for a first order reaction, like I said. Now also, solving for the concentration of A, then you have just the initial concentration of A times e to the minus Ka times T. And likewise, if you solve just this form for the natural log of A, concentration of A, then you have minus Ka times T plus the natural log of the initial concentration of A. These three are very important equations. So if you graph the natural log of A versus time, you've got a straight line, and the slope is just minus Ka. Alright, continuing on physical chemistry, chapter 17, section 3, we are still talking about first order reactions only. So here's another graph, concentration of A versus time. You notice it starts high at the initial concentration of A and gets lower and lower and lower. After a certain amount of time, you're going to have half as much. After the same amount of time, you're going to have half that. After another amount of time, you're going to have half that. After another amount of time, you'll have half that. So it's going to keep going to asymptotically to 0. But this is a good graph for finding half-life, because the half-life, it's going to be the exact same amount of time for any interval. So so that makes the math easier. So half-life, remember, when you're at the time, half-life is abbreviated T sub 1/2. So when you're at the half-life, that's T is equal to T 1/2. So the concentration of A is just going to be the initial concentration of A times 1/2. So that means that the initial concentration of A is equal to 2 times the current concentration of A when you're at 1/2, the first half-life. So just always keep in mind for these kind of reactions that the concentration of A, that's what you have left in the system. It's not what has departed from the system. So putting in that formula for rate we had before, instead of putting A over A naught, we substituted A naught. So we have the concentration, natural log of the concentration of A divided by 2 times the concentration of A. The concentration of A is cancel out, so you have the natural log of 1/2. And so just solve this for T 1/2. You're going to get T 1/2 is equal to 0.693 divided by the constant for A. This is only true for our first order reaction though. Now remember, 0.693 is a constant. This is a constant. And that's why for a first order reaction, our half-life is also a constant. Okay, continuing on physical chemistry, chapter 17, section 3. Now we're starting second order reactions. Now these are even more common than the first order, which are also pretty common. Now there are two types that we're going to look at. These aren't really the only types, but these are the two that make the most sense. So one is where you have A going to products, or two, when you have two different substances, A and B, going to products. Now we're going to assume the first type for now. We will do the second one later because they're both very important, very common. So the rate for this, we took out the 1 over A step already. So we have the differential of A over differential of T is equal to minus Ka times concentration of A squared. Remember, this is second order, so obviously there's a 2 in the exponent. And we want to integrate that. So after getting like terms on both sides, so we're taking the integral of the left side from the initial concentration of A to the current concentration of A of 1 over concentration of A squared times the differential of A, the concentration of A, equals minus Ka times the integral from 0 to T dt. So hopefully you remember integral of 1 over x squared is just minus 1 over x. So we have minus 1 over concentration of A, evaluated from the initial concentration of A to the final concentration of A. And then this is the same as all the other cases, minus Ka T evaluated from 0 to T. So this just gives us minus 1 over the concentration of A, double negative mix of positive, so we have plus 1 over the initial concentration of A equals Ka-T. Switch those around so it looks a little nicer. You get 1 over the concentration of A minus 1 over the initial concentration of A is equal to Ka times T. And remember, this is only true for a second order equation of the type we were talking about. Physical chemistry, chapter 7, section 3. So we are continuing order of the first type of second order reactions here. So here's a graph of 1 over the concentration of A versus time. Notice we're going to get a slope, a straight line with slope K. That's because if you solve for 1 over A, you get Kt plus 1 over the initial concentration. So this is your 1 over the initial concentration. This is a format of y equals mx plus b. M is the slope, so your Ka is the slope. And then, like I said, in this case, x are independent variables time, and then b is your intercept, which would be 1 over the initial concentration of A. Now for this type of reaction, the half-life, we're not going to derive that for you right now, we'll just give it to you. The half-life is 1 over the initial concentration of Ka. So that means if you want to know the half-life of a segment, you know the initial part of that segment times Ka. And so what this tells us, the half-life is going to keep changing because it depends on what concentration you start out with. So here's a graph showing the concentration of A divided by initial concentration of A against time. You notice, so it's going to ratio out. You're going to start out at 1 and get lower and lower. So here's a half-life. Here's another half-life, here's another half-life. It's going to keep longer and longer and longer. Still going asymptotically to 0, but it's going to be a little different from first order. The important thing is that each half-life is a different width. That's what, and it depends because for this half-life you use this A naught, for this half-life you use this A naught, for this half-life you use this A as A naught, etc. Alright, continuing on physical chemistry, chapter 17, section 3. Now we're talking about a second order reaction of the type where you have A plus B going to products. Remember this K up here, this is not a catalyst, that's the rate constant for this reaction. Now, we're going to assume that A and lowercase a, lowercase b, or nu1, nu2, the stoichiometric coefficients are equal to 1 for now. Now, the rate constant, the rate is R, is going to be equal to minus the differential of A, the concentration of substance A, divided by the differential of T. That's going to be equal to K times the concentration of A times the concentration of B. Move everything to the side so we can integrate. We have the differential of A divided by the concentration of A divided by the concentration of B, and that's equal to minus K dt. Now remember, we start out with a certain concentration of A, and we're going to take something away. That's going to be equal to the concentration of A. So this is like delta A or something. Same with B. We're going to start out with a certain concentration of B, initial concentration of B, and take something away. That's going to be equal to the differential of B, or equal to the concentration of B. Now we want to take the differential of this, so we get the differential to concentration of A is equal to 0, because this is a constant, minus dx. So we know that the differential to concentration of A is equal to minus dx. Now, what we're going to do, we're going to integrate from 0 to x, this difference, whatever it is, of dx. So we're going to have these up here. Oops, substitute in. So we're going to integrate the initial concentration of A naught minus x times the initial concentration of B, this isn't naught, initial concentration of B minus x. And that's still equal to the integral from 0 to t of k dt. Now to evaluate this, we're going to use the method of partial fractions. Okay, continuing on physical chemistry, chapter 17, section 3, we're still doing a second order reaction of the type A and B going to product. And remember how we said we had a integral of two variables, concentration of A, concentration of B. So we decided the way to integrate that is going to be with the method of two variables, whatever it's called. So we got this here. We have this fraction here, 1 over the initial concentration of A minus x times the initial concentration of B minus x. So we know that that's equal to 1 over the initial concentration of A minus the initial concentration of B times the whole quantity 1 over the concentration of B minus x minus the initial concentration of A minus x. Now we're going to integrate all this because it's the left-hand side of the previous equation we had, and it's the integral we're trying to integrate. So these initial concentrations, of course, these are constants. So these come out of the integral. And all that is times, we're going to do these integrals separately because they're separate volume. So we're going to integrate from 0 to x of dx over the initial concentration of B minus x minus the initial concentration, or the integral, definite integral from 0 to x dx of the initial concentration of A minus x. Now that's going to give us, remember, an integral of 1 over whatever is going to be natural log. So we've got, that's equal to 1 over the initial concentration of A minus the initial concentration of B times minus the natural log of initial concentration of B minus x, evaluated from 0 to x. And then plus the natural log of the initial concentration of A minus x, evaluated from 0 to x. So simply evaluating that, we get, I'll leave this constant the same, it's not changing. So minus the natural log of initial concentration of B minus x. And this quantity here, remember, we showed before at the previous slide, this is our concentration of B. Plus the natural log of the initial concentration of B. Plus the natural log of initial concentration of A minus x. And remember on the previous slide we showed how this is equal to the concentration of A minus the initial concentration of A. So we just substitute those in, and we still have the same factor out front. We get minus the natural log of the concentration of B, plus the natural log of the initial concentration of B, plus the natural log of A, minus the natural log of the initial concentration of A. All right, continuing on physical chemistry, chapter 17.3, or, well, 17, anyway. So continuing on the derivation we had before using integration, we just integrated, so now we put it back into the original equation after doing the integrals. So now we have 1 over the initial concentration of A minus the initial concentration of B times the natural log of this whole product quotient here, the initial concentration of B times the concentration of A divided by the concentration of B times the initial concentration of A equals KT. And then if we, I don't remember why, but we want to switch around the order here. So if we switch around the order here, basically divided by -1, so we flip this one upside down too. It means the exact same thing. So 1 over the initial concentration of B minus the initial concentration of A times the natural log of the concentration of B times the initial concentration of A divided by the initial concentration of B times the concentration of A equals KT. Now remember, that was when we assumed that the coefficients A and B were equal to 1. Now, if we did have coefficients A and B like this for products, then what we have to do, it ends up being almost exactly the same. The A ends up here, the B equals here. So you end up with 1 over the coefficient A times the initial concentration of B minus the B times the initial concentration of A times the natural log of the concentration of B times the initial concentration of A divided by the initial concentration of B and the initial concentration of A equals KT. So you think about it, if you multiply it by this term here, you're going to get another slope of Y equals mx plus B. So that's what we've done here. We've got this whole big thing here. This is our Y. And then, of course, t is our independent variable, time. So if we graph that, Y equals mx plus B, well, whatever let's see, this difference here, this will be our y-intercept actually. But the important thing here, our slope is just equals this. It's equal to the constant times the coefficient A times the initial concentration of B times the coefficient B times the initial concentration of A. So by doing this, at least you get a straight line. So remember, doing this from experimental methods, you can collect data points, fit it to a straight line. And just remember, before we had the stoichiometric coefficients, nu1, nu2, that's the same thing as the A, B. We just changed the nomenclature. That should be all for second order reactions then. All right, continuing on physical chemistry, chapter 7, more section 3. We're finishing up second order reactions. We're still doing the type where we have AA plus BB going to products. Now remember, before we talked about the half-life of a first order reaction, now we can have, or we also found this half-order, or the half-life of a second order reaction with only A going to products. But if you have this type of reaction, you can do it only if you have A equals B equals 1. Otherwise it makes no sense. Like if you have the initial concentration of B, 1/2 of that, and initial concentration of A, 1/2 of that, it doesn't even make any sense. So don't worry about it. All right, continue physical chemistry, chapter 17, section 3. Now we're talking about a third order reaction. Of course, there are a whole bunch of different types of those, but the only one we're going to bother with is the simple one, where you still have just one reactant going to products. So the rate law R for this is just going to be equal to a constant times the concentration of A cubed. And then, of course, is always, by definition, the differential of the concentration of A with respect to time. So, sparing in the math, the integrated rate law is 1 over the concentration of A squared minus 1 over the initial concentration of A squared, and that's equal to 2 kT. So, again, you can just solve that for 1 over A squared, and you have your Y equals mx plus B form. So you graph 1 over the concentration of A squared against time. You have a straight line. Notice you have a y-intercept. Your y-intercept, that would be 1 over the initial concentration of A squared. So you got a straight line, not through the origin, and your slope is just equal to 2k. This is physical chemistry, chapter 17, section 3 still. Now we're talking about a third order reaction. So we're only going to do the type where you have substance A going to product or products. So if it's third order, the derivative of the concentration of A with respect to time is equal to minus a constant times the concentration of A cubed. If you integrate that, it's really easy, so I skipped it. It's just 1 over the concentration of A squared minus the initial concentration of A squared is equal to 2 kT. This is the integrated rate law for a third order reaction of this type. So what this tells you, you just move this over here, you've got Y equals mx plus B. So you graph this 1 over concentration of A squared against time, lowercase t is time, you're going to end up with a straight line. It's going to have a slope of 2k. So this will give you a way to find your rate constant. So this straight line, though, does not come from the origin, though. The y-intercept is going to be the initial concentration squared, or 1 over the initial concentration of A squared. Continuing on physical chemistry, chapter 17, section 3. Now we're going to talk about any reaction of any generic n order, except for n equals 1. Remember, n can't be a fraction. It can be 1/2, 3/2. It can really be any, I think it has to be positive, but it can be pretty much any fraction. So we're only going to do the type where you have substance A decomposing into products. of the nth order. So the rate law would just be R equals K times the concentration of A to the n power because it's nth order. And remember, what we're going to do, it does not apply to n, it's not n equals 1, but we already did first order anyway. So that gives us the rate law. The derivative of the concentration of A with respect to time is equal to minus the rate constant times the concentration of A to the n power. So we're going to integrate this. Obviously we had to move A over here and move dt over here, so we have, like variables on opposite sides or whatever. So that gives us the integral from the initial concentration of A to the concentration of A to the minus n, since we moved it over, with respect to the concentration of A, is equal to minus the constant times the integral from 0 to t of the differential of t. So evaluating those, we get 1 over minus n plus 1 times all this quantity, the concentration of A to the minus n plus 1, minus the initial concentration of A to the minus n plus 1, is equal to minus kT. Obviously, if we want to simplify this, we're going to multiply it by 1 minus n, since, remember, this is minus n plus 1 is the same as 1 minus n, just rearranged. So that's going to give us the concentration of A to the 1 minus n, minus the initial concentration of A to the 1 minus n, and that's equal to n minus 1 times kT. Now what we want to do is divide by the initial concentration of A to the 1 minus n. Notice I didn't say we're going to add it, we're going to divide. Continuing on physical chemistry, chapter 17, section 3, we're deriving the rate law for reaction of n order. So we divide it by A naught to the 1 minus n, so we get, which simplifies to 1 here, so we get the concentration of A to the 1 minus n divided by the initial concentration of A to the 1 minus n, minus 1 is equal to n minus 1 times the rate constant K times t for time, divided by the initial concentration of A to the 1 minus n. Rearranging it a little bit, we get this ratio over here. The concentration of A divided by the initial concentration of A to the 1 minus n power is equal to the initial concentration of A to the 1 minus n power times n minus 1 times kT plus 1. Now this is going to be good for any order, even fractions like 1/2, 3/2, 7/8, whatever, except for n equals 1. So using that formula, solving for the half-life, it's just simple algebra, so I'm not going to show it. You get t 1/2 is equal to 2 to the n minus 1 minus 1 divided by n minus 1 times the initial concentration of A to the n minus 1 power times k. And that won't work for n equals 1, but it'll work for any other order. And so as an example, we already did second order, but to verify this formula works, you put in 2 for this, for n, you get the half-life t 1/2 is equal to 2 minus 1 over A naught k, which simplifies just 1 over A naught k. Okay, continuing on chapter 17, section 3. Now we're going to talk about what happens if you have a first order reaction, but it's reversible. Remember, before we did a first order reaction, but it was going only one direction, from the reaction to the product. So this is what it's going to look like. We have A going to C in some sort of equilibrium. Notice now we have two rate constants. We have Kf for forward, which is the rate constant for the forward reaction, and then we have K sub r, which is the reverse constant, or the rate constant for the reverse reaction. Notice sometimes you'll see a B for backwards reaction instead of R for reverse. So this is what's going to happen if you graph concentration versus JT. Now JT is just a constant of adding those two numbers. It's just to give you a time scale, it's kind of generic. So we're dividing by A naught here. So we're actually starting out the initial concentration A, it's going to be 1. And it's going to curve down over time. Now remember, with an irreversible reaction, it went the reactant eventually went down to 0 concentration. But instead here with a reversible reaction, we're going to level out, but it's going to be at some other concentration, the equilibrium concentration, which would only be 0 if it's an irreversible reaction. Of course, it can be higher or lower, it just depends on where equilibrium is going to be. Now, likewise, the product C, if we start out with no C, we start out here at the origin, and then again we divide it by A naught, just to put it on the same scale. So C is going to start at 0 and it's going to increase, and it too is going to level out. It's going to level out whatever concentration is going to be for equilibrium. So this is supposed to be horizontal, this is supposed to be horizontal. Now in this example, we just chose Kf divided by Kr to be equal to 2. That's what put this is up here. This doesn't have to be higher than that. If it has you can have equilibrium with a lot of A and hardly C, or you can have equilibrium with a whole bunch of C and hardly any A. It just depends on the type, whichever reaction we're talking about. So the rate of the forward reaction, of course, would be just the rate constant for forward reaction times the concentration of A. Because for the forward reaction, A is your reactant. So this is going to be the rate we're going to lose A. Now the rate of reverse reaction, then you use the other constant, the constant for the reverse reaction, and that'll be times the concentration of C. Because for the reverse reaction, C is your reactant, not your product. So the actual the concentration, the derivative of the concentration of A with respect to temperature, remember we're going to be losing A and we're going to be gaining A. So we're going to subtract out the A from the forward reaction and then add in the change in A from the reverse reaction. We're going to call this equation 1. But what we want to do is we want to find out a formula for the concentration of C and substitute that back in here. Okay, continue on physical chemistry, chapter 17, section 3. Now we're talking about a reversible first order reaction. So, since the stoichiometric ratios were the same, 1 to 1, we know the change in the concentration of C is equal to minus the change in the concentration of A. Remember, the change in the concentration of C is just the concentration of C minus the initial concentration of C. And likewise, the change in the concentration of A is just the concentration of A minus the initial concentration of A. So solving that for the concentration of C, we get the concentration of C is equal to the initial concentration of C plus the initial concentration of A minus the concentration of A. We'll call this equation 2. And we want to substitute this equation 2 into equation 1 on the previous slide. So we get the derivative of the concentration of A with respect to time is equal to minus the forward reaction constant times the concentration of A plus the reverse reaction constant times the initial concentration of C plus the initial concentration of A minus the concentration of A. Now let's see, what did we do here? So we did a little rearranging here. So we get the derivative of the concentration of A with respect to time is equal to the reverse rate constant times the initial concentration of C plus the reverse rate constant times the initial concentration of A minus the two rate constants added together times the concentration of A. We're going to call this equation 2A for future reference. Now remember, as time goes to infinity, the derivative of the concentration of A with respect to time is going to go to 0 because the system's going to reach equilibrium. Now remember, this won't mean there's no reaction. It means the forward reaction and the reverse reaction will have the same rate. So the concentration of A won't be changing anymore, and neither will the concentration of C, obviously. So from now on, we'll call the concentration of A the concentration of A at equilibrium because we're talking about what's going to happen at equilibrium. So that means that the rate constant for the reverse reaction times the initial concentration of C plus the rate constant for the reverse reaction times the initial concentration of A minus the two rate constants added together times the concentration of A at equilibrium is equal to 0. So obviously, just adding this term over here, we're going to get the reverse rate constant times the initial concentration of C plus the reverse rate constant times the initial concentration of A is equal to those two rate constants added together times the equilibrium concentration of A. We're going to call this equation 3 for future reference. What we want to do then is take this equation 3 and substitute in for 2A. Continue on physical chemistry, chapter 17, section 3. We're talking about equilibrium reaction, reversible reaction of first order. So now we have the derivative of the concentration of A with respect to time is equal to the two rate constants added together times the equilibrium concentration of A minus the two equilibrium constants added together times the concentration of A. So factoring out the Kf plus Kr, we get the derivative of the concentration of A with respect to time is equal to the forward rate constant plus the reverse rate constant times the equilibrium concentration of A minus the concentration of A. Now we want to integrate both sides. Of course, we'll have to get the A's over on the same side and so on. So we're going to integrate from the initial concentration of A to the current concentration of A with respect to the concentration of A, of 1 over the concentration of A minus the equilibrium concentration of A. And that's going to be equal to minus, you can pull out the two rate constants, Kf plus Kr, the integral from 0 to time of, well, with respect to time. So the integral of 1 over this is going to give us just natural log. So we get the natural log of the concentration of A minus the equilibrium concentration of A divided by the initial concentration of A minus the equilibrium concentration of A. And that's equal to minus the forward rate constant plus the reverse rate constant times time. Notice this equation's got three different concentrations for A: the initial concentration, the current concentration, and the equilibrium concentration. So if you're doing a problem, make sure you pay attention to which concentration goes where. So now we have the concentration of A minus the equilibrium concentration of A is going to be equal to the initial concentration of A minus the equilibrium concentration of A times e to the minus jt. So J, we defined on a previous slide, is the forward and reverse reaction rate constants added together. So go back to that slide with the graph and it'll make more sense. And likewise, remember equation 3 on a previous slide, that's how you can find the equilibrium concentration of A. Okay, continuing on physical chemistry, chapter 17, section 3, we're finishing up the equilibrium constant reactions of first order. So here's a graph of the concentration of A against time. No matter what, you're going to start out the initial concentration. It's supposed to be A9 here. So if it's first order irreversible, it's going to come down, it's going to go asymptotically to concentration of A equals 0. If it's an equilibrium reaction, then it's going to come down, it's still going to be asymptotic, but it'll be a different concentration, just depending on where equilibrium is. So this horizontal part, where it's asymptotic, that's the equilibrium concentration of A. Now if we take the stuff we just derived, and we set the equilibrium concentration of A equal to 0, and the reverse rate constant equal to 0 for first order, then it simplifies to just the concentration of A is equal to the initial concentration of A times e to the minus kT, where K is the forward reaction. So this is just to show that this will simplify to this, like you would hopefully expect. If you continue on physical chemistry, chapter 17, section 3, now we're going to talk about what happens when you have consecutive reactions. For example, reactant A goes to product B, but then product B becomes a reactant to go to product C. Notice we're going to have two different rate constants, K1, K2. Now that we're going to assume these are all first order irreversible. So we have one rate law that says the rate of equation 1 is just the equilibrium constant for equation 1 times the concentration of A, because A is the reactant for that. And so we have A, so that's for this left reaction. And then we have the other rate law for this right equation that says, okay, this K2 constant is equal to this concentration of B, because B is the reactant for this equation. And that's for that equation. So now we have, for B, we're gaining B at the rate of K1 times the concentration of A, but we're also losing B at a rate of concentration of K2 times concentration of B. We're going to write this equation 1 and 2 for future reference. So the actual change in concentration of B would be these two added together. So we have K1 times the concentration of A minus K2 times the concentration of B. Now, what that really gives us then is three equations. The overall rate of gain for A is just minus K1 times the concentration of A. We'll call that equation 3. And the overall gain for substance B is just K1 times A minus K2 times B. And then for C, it's going to be just K2 times B. We'll call it equation 5. Now remember, our initial conditions, to make it simpler, we're going to assume we have no B and no C. We're going to start out only with A. Continue on physical chemistry, chapter 17, section 3. So then from equation 3, we're going to get the concentration of A is equal to the initial concentration of A times e to the minus k1t. We'll call this equation 6 for later use. So now we have the derivative of the concentration of B is equal to K1 times the concentration of A minus K2 times the concentration of B. Because I think we had that from before. But this is a linear differential equation, first order linear differential equation. Differential equation isn't a prerequisite for this, but it'll help you understand. So we're going to get the derivative of concentration of B with respect to time is equal to the rate constant 1 times the concentration of A times e to the minus kt. Oops, I think that should be k1t. And then minus k2 times the concentration of B. We'll call that equation 7. So now we want to let concentration of B equal to u to the e to the minus k2t. And then, oh yeah, because of, that should be 2, k1. Well, let's go with this, see what happens. So we're going to use the chain rule to find the derivative of that. So we get the derivative of concentration of B with respect to time is equal to minus k2 times u times e to the minus k2t plus e to the minus k2t times the derivative of u with respect to t. Now what we want to do is substitute for the concentration of B into equation 7. So that gives us k2 times u times e to the minus k2t times du dt minus k1 times a naught times e to the minus k1t equals 0. What we want to do is solve for this du dt. Continuing on physical chemistry, chapter 17, section 3, we're talking about two consecutive reactions, A going to B, going to C irreversibly. So now we have the derivative of u with respect to t, time, is equal to k1 times a naught times e to the minus k1t divided by e to the minus k2t. So obviously flipping this upside down, turning it to a positive k2, we get that's equal to k1 times a naught times e to the k2 minus k1t. So solving for du, we get du equals k1 times a naught times e to the k2 minus k1t dt. Now we've separated variables so we can integrate. So we're just going to integrate what we just had. The result is that u is equal to k1 times a naught over k2 minus k1 times e to the k2 minus k1t plus k1 times the concentration of A times c. C is an integration constant. So we're going to have to figure out what that is. So solving for B, or well, what we had before, we get the concentration of B is equal to u times e to the minus k2t. So substituting all that in, we get k1 times a naught over k2 minus k1 times e to the k2 minus k1t plus k1 times a naught times c times e to the minus k2t. So this is the general solution. If you had differential equations, you know what that means. So now we need to find our particular solution, which means we need to find c. Continuing on physical chemistry, chapter 17, section 3, we're still talking about two consecutive reactions, substance A going to B and then substance B going to C. So remember what we said before, at time equals 0, we're going to have concentration of B equals to 0, because we're going to just start out with only the original reactant, A. So we'll just set that equation for B equal to 0. So we get 0 equals K1 times A naught over K2 minus K1 plus K1 times A naught times C. And this is integration constant C. This isn't substance C. We're only talking about A and B for now. So this, solving for C, we just get minus 1 over K2 minus K1. So we can put that back in here. Concentration of B equals K1 times A naught over K2 minus K1 times e to the minus K1t plus K1 A naught times e to the K2t times 1 over K2 minus K1. Moving this down here then, we get concentration of B is equal to the rate constant for equation 1 times the initial concentration of A divided by the rate constant for equation 2 minus the rate constant for equation 1 times the natural number E to the minus rate constant for equation 1 times time minus the rate constant for equation 1 times the initial concentration of A minus the rate constant for equation 2 minus rate constant for reaction 1 times e to the minus rate constant for reaction 2 times time. Notice this is the same term, so we can factor that out. So we get the concentration of B is equal to the rate constant for reaction 1 times the initial concentration of A divided by the rate constant for equation 2 minus the rate constant for reaction 1 times e to the minus rate constant for reaction 1 times time minus e to the rate constant for reaction 2 times time. We're going to call this equation 8 for future reference. So this is our particular solution for the concentration of B. And that's what we were trying to find, so we're done. Continue on, physical chemistry, chapter 17, section 3. We're still doing sequential first order reactions, non-reversible, irreversible, A to B to C. So we just showed how to find the concentration of A, concentration of B, or well, the derivative with respect to time. So now we want to find the derivative of C with respect to time. Now the most obvious way to do it would be to take that equation we just found, equation 8, and substitute it in for here, for the concentration of B. But that's actually the hard way, because then you'll actually have to integrate, do calculus. The easy way is just use conservation of mass. We know, since we started out with only A naught, B naught, and C naught were 0, all the amount of substance, A plus B plus C, is equal to the initial amount of substance we had, A. So since the stoichiometric ratios here are 1 to 1 to 1, we're not going to worry about lowercase a, lowercase b, lowercase c. So the reaction will work just like we have it here. So solve for the concentration of C, we just get A naught minus A minus B. So integrating that, we're going to get, or no, we're not even integrating, we're just substituting on what we found before. So the concentration of C is just equal to the initial concentration of A minus the initial concentration of A times e to the minus K1T minus K1 times A naught over K2 minus K1 times e to the minus K1T minus e to the K2T. Now first we want to factor out the A naught because it's in all three terms. So we get the concentration of C is equal to the initial concentration of A times 1 minus e to the minus K1T minus K1 over K2 minus K1 times e to the minus K1T plus K1 over K2 minus K1 times e to the minus K2T. Now what we want to do is get a common denominator here. So all these, K2 minus K1, K2 minus K1, we want a K2 minus K1 here. So the initial concentration of C is equal to the initial concentration, the concentration of C is equal to the initial concentration of C times 1 plus K2 minus K1 times e to the minus K1T minus K1 times e to the minus K1T plus K1 times e to the minus K2T. And all that, except for the 1, is over K2 minus K1. Continue on physical chemistry, chapter 17, section 3. We're just finally finishing up the section about A goes to B goes to C, consecutive reactions. So finally simplifying concentration of C equal to A naught equals 1 plus minus K2 times e to the minus K1T plus K1 times e to the minus K1T minus K1 times e to the minus K1T plus K1 e to the minus K2T. Notice these two add up to make 0, so you're left with just these two end terms. So simplifying, we get concentration of C is equal to the initial concentration of A times 1 minus K2 over K2 minus K1 times e to the minus K1T plus K1 over K2 minus K1 to e to the minus K2T. Now, let's suppose that K1 is equal to 6 times K2 as an example. So we're going to graph concentration versus K1 times time here. So we're going to start out with A naught, obviously, and A is going to go down asymptotically to 0 because it's an irreversible reaction. Now B, we start out with nothing, but as there's more and more A, B is going to go faster and faster until B gets to a maximum point wherever there's enough A to make this go. And then eventually, as you run out of A, then you'll run out of B too, and then B will also go down asymptotically to 0. And then finally C, it too is going to start out pretty slow because there won't be any B, but as A builds up and A is used up to become B, eventually C will pick up, and eventually at the end, you should be left with just pure C. Continue on physical chemistry, chapter 17, section 3. Now what happens if we have two competing reactions? Let's say A can become C, or A can become D. Well, then you'll have a rate constant for with this reaction, K1, and you'll have a rate constant for this reaction, K2. Now we're going to assume for now that both reactions are irreversible in their first order. Now, one example would be taking toluene and making nitrotoluene. You'll actually get 3 isomers, the ortho, para, and meta. But to keep things simple, we're going to look at just 2 of the isomers for now. So for the A, our toluene, the derivative of the concentration of A with respect to T is just going to be equal minus K1 times the concentration of A minus K2 times the concentration of A. So, in other words, we're going to lose to this reaction and to this reaction. So that's going to be equal to just minus K1 plus K2 times the concentration of A. So just integrating that isn't really too hard. You just get the concentration of A is equal to the initial concentration of A times e to the minus K1 plus K2 times T. This is the integrated rate law, but only for our substance A, of course. So what about concentration of C over time? Well, the derivative of concentration of C with respect to time is just K1 times A. So then we could just get K1 times A naught times e to the minus K1 plus K2T. Yeah. Okay, so then moving dt over here so we can integrate, we get the derivative of concentration of C is equal to K1 times A naught times e to the minus K1 plus K2 times T with respect to T. Okay, continuing on physical chemistry, chapter 17, section 3. So now we're going to integrate that. So we get the integral of the differential of concentration of C is equal to the integral of K1 times the initial concentration of A times e to the minus K1 plus K2T dt. Integrating that, we just get the concentration of C is equal to K1 times the initial concentration of A times this entire quantity here. We get minus 1 over K1 plus K2 equals e to the minus K1 plus K2T plus I. I is an integration constant. Obviously, normally you use C for integration constant, but C is already taken for our substance, so we use something else. Now remember, at time equals 0, we said that we only have pure A. We don't have any C or D. So the concentration of C is equal to 0. So we can use that to find the value for I. So we're just going to set this equal to 0. So we get 0 is equal to K1 times A naught times minus 1 over K1 plus K2 plus I. So we know that K1 is not equal to 0, and we know that A naught is not equal to 0. Therefore, this other term here must be equal to 0. So solving for that, we get I is equal to 1 over K1 minus, or K1 plus K2. So the initial concentration of C is equal to K1 times A naught times minus 1 over K2, K1 plus K2 times e to the minus K1 plus K2 T. And then, this should be plus our constant I. So simplifying then, or factoring out whatever the K1 over K1 plus K2, we get the concentration of C is equal to K1 times the initial concentration of A over K1 plus K2 times this whole quantity here where we get 1 minus e to the minus K1 plus K2T. Continuing on physical chemistry, chapter 17, section 3, and we're still talking about 2 competing reactions, both of them irreversible. So like how it said, the same way we got concentration of C, the concentration of D comes out to K2 times A naught over K1 plus K2 times 1 minus e to the minus K1 plus K2T. Now if we graph the concentration versus K times time for all 3 of these, where K is just K1 plus K2, well, A, of course, starts at the top because it's the reactant, and it's going to come down all the way down to 0 because it's, well, this is irreversible. And then C and D, they're both going to start at the bottom and they're going to curve up. And in this case, since K2 or K1 is higher than K2, C is going to form faster than D. So this is arbitrary. Obviously, you can have 2 different numbers for K1 and K2. You could have them exactly the same, and all it's going to do is shift exactly how C and D are related to each other. Now, remember back to the rate laws we derived, equation 1 and equation 2. If we divide those, we have a formula for the concentration of C divided by the concentration of D, and that's just K1 over K2. So if we take this concentration of C divided by concentration of D, we're going to get K1 over K2. And I didn't draw it very well because it should be 2, because I said that K1 is equal to 2 times K2. But remember, these lowercase k's we're saying are the rate constants. Now if we have a reversible reaction, then for the forward reaction A to C with constant K1, the reverse reaction is going to have constant -1. And likewise for the forward reaction A to D with constant K2, then you'll have the reverse reaction with constant K-2. All four of these constants, though, remember, are the rate constants. All right, continuing on physical chemistry, chapter 17, section 3. We're talking about two competing reactions and what happens if they're reversible. So now we have A in equilibrium with D and A in equilibrium with C. So we have an equilibrium constant for each of those reactions. We have for the first reaction, we have capital K sub 1, the equilibrium constant for A in equilibrium with C. And then for the second reaction, we have capital K sub 2, the equilibrium constant for the second reaction, A in equilibrium with D. Now, if we divide those two, capital K by capital K1 by capital K2, remember, the equilibrium constant is the concentration of the one divided by the concentration of the other. So we get, for the first reaction, K1, we get concentration of C divided by the concentration of A. And then for the other equilibrium, K2, we have the concentration of D divided by the concentration of A. The concentration of A's are going to cancel out because it's all in one solution or whatever, one reaction. So we have the concentration of C divided by concentration of D. This is as temperature or time approaches infinity. In other words, we're at equilibrium. In fact, I was almost tempted to put equilibrium subscripts here, but that's redundant. It's saying it's at equilibrium. So it's important to realize, though, these can be competing, though. One product can be favored thermodynamically, but the other kinetically. For example, if lowercase k1 divided by lowercase k2 is much greater than 1, then the concentration of C will be greater than concentration of D. That means that product C is favored kinetically, which all that means is that it has low activation energy. So you can have the reaction at low temperatures, high rate of reaction. On the other hand, if you divide capital K1 equilibrium constant by K2, and that's much less than 1, then that means the concentration of D is going to be much greater than C, concentration of C. That tells us that D is favored thermodynamically, which means that D is a more stable molecule or whatever than substance C. Now, what that tells us then, we actually have a choice of products, C or D. All we have to do is control the reaction conditions. You control temperature, pressure, etc. We'll get into the details later. And then you can choose, do you want a lot of C or do you want a lot of D? Okay, continuing on physical chemistry, chapter 17, section 3. We're talking about two competing reactions. We've been talking about how a reaction can have one product that's kinetically favored and a different product that's thermodynamically favored. And you're probably wondering how in the world that's possible. So this is the slide to try to explain that. We have this reaction here. We've got this long molecule here. Notice it's got two double bonds. And we're going to add HBr. And that's going to be in a reaction with two different products. We're going to add the bromine here and a double bond over here. Or we'll add the bromine here and a double bond right next to it. So this one over here, hang on a second, let's start over.